Hello, my name is Seyerlein, and over the next few minutes I would like you to have a look with me on my poster about the question: are contaminated eggs a potential source of minute amounts of clomiphene in doping control samples? So let's start with the introduction. Clomiphene is a selective estrogen receptor modulator and is therefore banned in sports by WADA at all times. The anti-estrogenic effect of clomiphene tends to be abused in doping mostly to prevent or mitigate side effects of anabolic steroid abuse. The number of adverse analytical findings of clomiphene has continuously increased since 2011. This may be due to improved analytical sensitivity, but contamination of food could also be the cause, because therapeutically clomiphene is prescribed to women suffering infertility to induce ovulation, an effect which has also been shown in studies on hens. When hens were treated with clomiphene, an increased egg production rate was observed. This brings us to the question: can traces of clomiphene be found in the eggs of hens given the drug? If this is the case, these trace amounts could lead to adverse analytical findings in doping control samples, a potential problem which we were tackling with this project. The study consists of two parts. First, an animal administration study was conducted by our collaboration partners in Belgium. In this study, 24 laying hens were given 10 milligrams of clomiphene citrate daily for 28 days. This is the dose determined to be effective for chickens. During the study, the eggs were collected as they were laid, before, during, and up to 2 weeks after the 28-day period. The eggs were then either analyzed directly or sent to us to Cologne for the second part of the project. In this consumption study, each volunteer ate 2 clomiphene-containing eggs, and a comparative study was also conducted with microdoses of 1, 10, and 50 micrograms clomiphene citrate. Subsequently, they collected urine for 3 weeks, which was then tested for clomiphene by means of HPLC MS. So let's move on to the results. The eggs were extracted with acetonitrile and measured by HPLC MS. Here you can see the clomiphene levels we determined over time. As you can see, the first clomiphene residues in the eggs were found after 2 days already. And after the 28-day period, the concentrations in the eggs decreased again. Aside from clomiphene, we found that the main metabolite hydroxyclomiphene was also transferred into the eggs. Compared to clomiphene, lower amounts were detected. This result is an important indication, as it already shows a first difference to the uptake of clomiphene as a drug. Also important to note is that clomiphene is present as E-clomiphene and Z-clomiphene, but in the eggs we almost only found the Z forms. So let's move on to the second part. The urine samples were hydrolyzed and extracted by a liquid-liquid extraction, which is the standard procedure for clomiphene in doping control analysis. In the urine of all volunteers, the intake of clomiphene could be detected. In this bar chart, you can see the maximum concentrations of hydroxyclomiphene that were excreted. And here at the top, you can see the EICs of the standard references from clomiphene and the 4-hydroxy metabolites. The center graph shows a sample after egg consumption, and the bottom one a microdose sample. This shows that the consumption of eggs containing clomiphene could indeed result in an AAF in a doping control. Therefore, we wanted to develop a method to differentiate the uptake pathways of clomiphene. So the next step was to look at the intake phase 2 metabolites. The analysis followed a simple SPE purification without hydrolysis. We found that the peaks of the 2 samples in the EIC of the glucuronide had slightly shifted retention times. Also, these peaks had different mass spectra. So this meant that in one of the samples, the hydroxy group must be located elsewhere. And besides the 4 hydroxy metabolites, previous studies have also described 3 hydroxy metabolites, sometimes even as the main metabolite. So my first guess was that this could be the wanted metabolite. So I improved the separability by implementing a derivatization step with denser chloride. Compared to the previous methods, it was now possible to separate the 4 different hydroxy metabolites, as you can see here. And here at the top chromatogram, the middle clearly indicates Z4-hydroxyclomiphene to be in urine after egg consumption, and the bottom one indicates that after intake of the microdose, E3-hydroxyclomiphene is excreted. To compare the samples and the way of clomiphene intake with each other, the distribution of the peak areas of the different hydroxy metabolites is plotted here. These are random samples from all volunteers. We see very clearly that all volunteers who ate eggs contaminated with clomiphene excreted over 90% Z4-hydroxyclomiphene, while the distribution in urine of volunteers who received the microdosing differed significantly from them. This already brings me to the summary of my presentation. When laying hens are administered clomiphene, residues can be detected in eggs, and consumption of these contaminated eggs can be detected in the urine and therefore could result in a clomiphene AEF during a doping control. But if the formed hydroxy metabolites are analyzed by the method presented here, a characteristic pattern emerges for the urine samples after consumption of contaminated eggs, which could not be found for the microdoses. So, and finally, I would like to thank everyone who has contributed to this project and you, of course, for listening.